Righty, let's look at section 2.31, direction fields. And so with this is a graphical approach. I'm going to say graphical / numerical approach. To ODEs and actually PDEs, partial differential equations as well. But so here the idea is, if I'm given, say, a differential equation, and let's see, they have this one. This is on page 46. They say u prime of t is equal to minus k times u minus a of t. Okay, now they tell us k is 0.2 and a is a function that they give us, so this is minus 0.2 times u minus 10 minus 5 sine of t over 2. Okay, so the idea is I could get some sense of what this looks like, because at any given value of t and u, I can use this to compute the derivative, right? So if I have a t and a u, this is a lot like, your usual t-chart to just plot a function, but here we're going to toss in u prime. And so suppose I let t equal 0 or 1 or 2, and I let u equal, well, and actually let's change that. Let's let t equal 0 or 0 or 0, and let's let u equal 0 or 1 or 2 to start with. Then as we look at u prime here, we see that we would get minus 0.2. U is 0, so I'd have a 0. And then minus 10. And then sine, 5 sine 0. And so we'd get a 0 there. And so I guess that is 2. And then at u equal 1, we would get minus 0.2, 0, not 0, sorry, 1, minus 10, 0. And so we would get 1.8. And then at 2, we'd get a minus 0.2, a 2, a minus 10, 0 there. 1.6, and let's do a couple more. 34. Here we get 1.4 and 1.2. Okay. Then, suppose I went with t equal, what could I do very easily? How about t is 60 degrees or pi over 3? So pi over 3 and down, and then a 0, a 1, a 2, a 3, a 4. Well, then I would have my minus 0.2, 0, minus 10, but then minus 5 times sine of pi over 6. And well, sine of pi over 6 is a half. And so we get minus 15, or sorry, minus 12 and a half times a negative 0.2. And so I guess that's 2.5 maybe. And then at 1, minus 0.2, 1, 10, minus 5 sine pi over 6. And so that will be 2.3. And then I'll get 2.1, 1.9, I guess, and 1.7. Okay, so what I'll do now is I have these points here, 0 and pi over 3. So here's t. And then at each of these, I have u at 1, 2, 3, and 4, and 1, 2, 3, and 4. So those are the 10 points in the Cartesian coordinate system that I created up here. But now, what I'll do is, at each of those points, I'll draw a short little line that sort of has the slope that I got here. So I had a slope of 2, and it went down by 0.2 as I went down. So 2 would be pretty steep looking slope, a little bit less, a little bit less, a little bit less, maybe, if I'm drawing very well, and something very close to 1 there. And then a steeper slope yet here. That was a 2.5. And then 2.3, 2.1, 1.9. So as you can tell, if you're doing this by hand, you're probably not going to do a great job if the slopes are all pretty similar. But that's the idea, and what I could kind of gather from here is if I'm sort of connecting the dots, maybe if I had a solution that went through 0, 0, maybe I can tell that solution would go up something like that. So you see, that's where I say this is graphical, because I'm looking at a picture, but it's also sort of numerical, because what I've done is I've just at lots of different numerical points, I've computed the derivative using the differential equation. Okay, so I know what the derivative is there, and so I've just made little tiny dashes to try to create a derivative map, I guess you could say, in the Cartesian coordinates. But then if I kind of look at those and try to connect the dots, then, you know, I've got some idea of maybe what different solutions look like. All right, and that's all one of these graphs is, a direction field. It can also be called a slope field because you're making a bunch of slopes. Now, I did not put directions on these, making it a true direction field, but we'll show you a code that will do it. And if you put little arrows on there, all right, we'll get those arrows, and there, you know, and those would be directions that the solution is going. All righty, so that's a direction field.